Welcome to our first ClimTip webinar. For those of you who are new, ClimTip is a Horizon Europe research project funded by the European Union, aiming to improve our understanding and knowledge on climate tipping points and their impacts. We have a diverse expertise from our partners from all around Europe and the world, and the project is led by us at Technical University of Munich and my colleagues Nicholas Boas and Sebastian Battiani. And this webinar series we planned as a space to share the latest research related to climate tipping points and have this discussion public. And today we start our first one on the relationship between the deforestation and climate. And I will let Nicholas introduce our guest today.
Yes, thank you very much, Kurt. And so hi on my side. Thanks for joining. So numerous. Really happy to see that. And yeah, so we're going to do this once a month, as Kurt said. And today, the first iteration, it's a really great pleasure and honor to have Dominick Spracklen as our first speaker. Dominick has obtained a PhD from the University of Leeds in 2005, working on aerosols, and is now a professor of biosphere-atmosphere interactions, also at the University of Leeds. And he has, for his really interesting work, he has been awarded numerous prestigious prizes, like the Philip Leverhulme Award in 2016, I think, and is currently running an ERC Consolidator grant, also to study impacts of tropical deforestation and regional climate. And yeah, so as also in ClimTip, one of the big focus component, like one of the components of the Earth system that we put a lot of focus on is the Amazon. It obviously has very strong interactions with the atmosphere and is sort of, yeah, I mean, maybe like one of the archetypes of what we might call tipping elements in the Earth system. And Dom really is an expert on this, and so I'm very much looking forward to this talk. Dom, the floor is yours.
Thank you, Nicholas. Can you hear me?
Very well.
Brilliant. Well, thank you very much for the invitation, and thank you everyone for joining online. I'm really looking forward to talking about our work today. I'm actually on field work this week in the woods in Western UK. So we're on satellite Wi-Fi. So I'm hoping it's going to hold up and work. But if we have any problems, that's why. So yeah, so I wanted to talk about some of the work we've been doing as part of that consolidated project, looking at the impacts of tropical deforestation on local and regional climate. And for this talk, really talk a little bit about how that might have implications for climate tipping points, specifically in the Amazon. So I should say the people that have done all this work, Callum Smith, he's a PhD student. He's working on our consolidated project and is now a postdoc working on a project in collaboration with Brazil. Yu Liu, who's a PhD student between Nanjing and Leeds. Ed Butt, who is now working on a new project we have looking at regional impacts of deforestation. And Jess Baker, she was working with me as a research fellow, but now has her own UKRI Future Leaders Fellowship, which is going to be looking at some of these local and regional impacts of forest on climate, but looking at the different direction, how reforestation and restoration of forests might be able to reverse some of these climate impacts. And she may have some postdoc positions available coming up in the next few months. So if you're interested in this work and looking for a position, that might be a great opportunity. So this picture here shows one example of what tropical deforestation looks like in the flesh. So we have mature tropical forest in the background, and a recently area of cleared forest in the foreground. So it's quite a good example to kind of see what it looks like, but it's also a good picture to kind of illustrate some of the differences between a mature forest and an area of deforested land that can have some of these climate impacts. So the mature forest in the background stores a lot of carbon in the trunks, and that carbon is released when the land is deforested and the trees are cleared. And that's one way that we often think about in terms of deforestation impacting our global climate. And about 10% of anthropogenic CO2 emissions come from deforestation, and most of that from tropical deforestation. But this land use change also has some very other important impacts on climate. And one way is through how the different land covers have different brightnesses. So you can see that the background, the forest is quite dark, and the foreground is much brighter. And that's because of different albedo of those surfaces. And that changes the amount of energy that the different surfaces reflect back into space. And that has a direct impact on the relative balance of the atmosphere, and has a direct impact on local climate. There's also a big difference in terms of the amount of moisture that the surfaces put back into the atmosphere. So because the forests have deep roots, because they're doing a lot of photosynthesis, they transpire a lot of moisture into the atmosphere, so pump moisture from the soil into the atmosphere. And that has two important impacts. First, it moistens the atmosphere, but second, it also changes the amount of energy that goes into heating the atmosphere as sensible heat versus the amount of energy that's evaporating that moisture as latent heat. And changing that ratio also has very important impacts on kind of local temperature. And maybe the third way is how the different land surfaces interact with air moving over the surface. So in the background, the trees have a canopy of 20 or 30 meters high, and that's going to interact with that air moving over the surface in a very different way to the much smoother surface that we see in the foreground. And again, that's going to change the flow of air over the surface and going to impact the atmosphere at local to regional scales. And so this sort of schematic here shows some of those impacts going from a kind of local scale impact on climate, where changes in that heat balance at a local scale, patches of warm ground where the land has been deforested, contrasting with cooler land where the trees still exist, can create convection at those forest and non-forest boundaries that can potentially cause increases in rainfall. When we get to slightly larger scales, that reduction in the amount of moisture that's being pumped into the atmosphere can reduce moisture in the atmosphere, reduce moisture recycling. And we know in places such as the Amazon, about a third of the rainfall is coming directly from the forest itself through this precipitation recycling process. And so through reducing that moisture input into the atmosphere, we can start to reduce precipitation at that regional scale. And at even larger scales, then we can start to impact the circulation of the atmosphere, how air is moving across very large parts of forest at kind of regional continental scale. And then potentially, if we're changing the climate at those larger scales, then that can then feed back in on this atmosphere vegetation system. And so this was the work that came out, very nice work came out last year, which was looking at links between as you start to deforest the Amazon, that impact that can have on the regional precipitation, regional rainfall across that region, that can then feed back on mortality of the vegetation, additional vegetation, death of that vegetation that can then lead to further impacts on climate. So this sort of kind of positive feedback between deforestation, climate, leading to additional forest loss. I'm just going to see whether I can get rid of this top there. So in this talk, I want to talk about three different aspects of work we've been doing, which is going to be moving through these different scales. So first, looking at, can we observe the impacts of tropical deforestation on local rainfall? Second, can we detect non-local impacts of tropical deforestation on climate? And third, as we move to those larger regional scales, can we start to think about how tropical deforestation can impact atmospheric circulation and regional climate? So the impacts of tropical deforestation on rainfall are still really highly uncertain. And the plot on the left shows a synthesis of a range of observational studies that looked at how rainfall might be modified over a deforested region in comparison to a forested state. And here they suggested that small amounts of deforestation could lead to increases in rainfall, and this could be due to that changing the heterogeneity of the land surface, kicking off convection that could cause additional rainfall of those relatively small amounts of deforestation. But that as that deforestation extent increases, then we might expect rainfall to be reduced. And on the right, showing a similar thing, so change in rainfall on the y-axis and amount of deforestation on the x. But here is synthesis of different climate model studies, showing that in those climate model studies, we tend to see larger reductions in rainfall as we increase that deforestation extent, but there's very wide uncertainty across those different models. So if you look at the kind of right-hand edge of this plot, even very large reduction of Amazon forest in some models leads to virtually no change in rainfall, whereas in other models we're predicting sort of 40 to 50% reduction in rainfall. So we wanted to see whether we can use the recent satellite and data record over the last few decades to see whether we can observe an impact of tropical deforestation that's occurred over the last few decades on local precipitation, and whether we can start to see, get a better quantification of what the likely sensitivity of tropical rainfall to.
Is it okay to interrupt with questions?
You what, sorry?
Is it okay to interrupt with questions?
Sure, yeah.
I was just wondering before when you said the reduction due to deforestation of precipitation, is that in exactly the same area or is it over a different area? Since you could imagine that due to sort of prevailing winds, that it should not be exactly where the deforestation is, that the reduced wind precipitation is.
Yeah, it's a good question. So I think there's a range of different scales that are happening. So what I'm about to talk about here is looking directly over the region of deforestation. So it is looking at that. How is the deforestation impacting local precipitation directly over that region of deforestation? But there will also be, as you say, that sort of downwind impact of the deforestation on moisture further at a kind of regional scale. So here we're sort of trying to separate those out. And because of the different mechanisms through which forests and deforestation could impact precipitation, we might expect things to happen at those different scales. So here what we did was took the change in forest cover that's happened over the last few decades, so from 2003 to 2017 from satellite data, and then we overlaid that with change in precipitation from different gridded data sets. And because we're trying to remove any regional climate signal that might have happened that's not due to deforestation, due to regional climate variability or due to global climate change, then we use the sort of nearest neighbor approach that I show on the right here, where we look at the change in precipitation over a region of deforestation, and then we look at the change in precipitation over a nearby area of forest that hasn't experienced any forest loss, and then we subtract those one from the other, as shown at the bottom, and that gives us the change in precipitation that's due to the deforestation signal. And so when we do that, these are the results here. So showing change in precipitation as a function of forest loss, so that's the precipitation change per percentage point of forest loss on the y-axis, and then different scales on the x-axis. And so here you can see going from about a 5-kilometer scale on the far left up to a 200-kilometer scale on the far right. So here we are sort of moving across those sort of scales from a very local impact through to a bit more of a regional impact on the right. And what we see is in the satellite data, we see a kind of robust reduction in precipitation over regions of deforestation, particularly at scales above about 50 kilometers. But interestingly, we see diverging results in the station data and also the reanalysis data. So the station data is coming mainly from rain gauges, which you might expect that data to be the most reliable in some ways. But we think in the tropics, because the data record is very sparse and there's a lot of smoothing between the available station data, that doesn't give you a very good record of what's actually happening over regions of forest loss. We sort of see a similar thing in the reanalysis data, that that also doesn't see the same signal as we see in the satellites. And again, we think that's largely due to poor space data availability in the tropics. If you look at the same thing, but looking across different seasons, we see robust reductions in precipitation, both in the dry season and in the wet season. And on an annual scale, we see a reduction of about a 10% reduction in local annual mean precipitation for large-scale forest loss. So that sort of fits somewhere in that that reduction that we saw in the climate models, and starts to give us maybe a sort of indication of the kind of the scale of reduction that we're seeing from observational data. But then this is sort of starting to think a little bit broader about what might the regional impacts might be. In the method that we've used this nearest neighbour approach to look at what's the impact over the region of deforestation, so that's shown in the middle here, and then we subtract any signal that we see over a region of forest, and we assume that that's due to climate variability or due to global climate change, and then the signal that we get is the difference between the two. However, if deforestation is also causing some either drying or warming in surrounding regions, and those surrounding regions of forest. And so that's what's shown on this right-hand side here. So we've got this sort of this warming here, which is caused, or warming or drying, which is caused by the deforestation itself. Then when we subtract this signal over surrounding regions of forest, we're going to be underestimating the impact of the deforestation, because we've subtracted that regional response that deforestation is having. So we wanted to look at whether we could see any evidence of this happening, and so we looked. I did a focused study just on the Amazon, and here we, instead of looking at precipitation, we started to first look at temperature, because we think it's an easier signal to see in the climate data in terms of temperature. And so here you see observed forest loss on the X over about a 20-year period, and then the observed land surface temperature change from satellite on the right. And you can see very clearly where there's been regions of strong deforestation. You see on the left, you see a very clear warming in the land surface temperature signal. But what we wanted to do was kind of look at this data to see whether we could isolate regions where there's only been local forest loss, so only forest loss in the kind of 1 to 2 kilometer pixel area, but no forest losses at regional scales, and then look elsewhere where we could find regions where there'd been local forest loss, but also regional forest loss at 2 to 10 or 2 to 100 kilometer scales. And then we wanted to look at what was the warming across those different categories. And so when we did this is showing on the left here the land surface temperature warming for different amounts of local deforestation. And so you can see that areas that experienced small amounts of local deforestation only warmed by about 0.3 Kelvin over this period, but areas with stronger local forest loss warmed by about 1 Kelvin over this time period. But then if we compared that to regions which experienced the same amount of local forest loss, but then also experienced regional forest loss, you can see that that warming starts to get stronger in these regions. And then if we also look further at regions that had local forest loss, but also regional forest loss out to about 100 kilometers, then you can see the warming that those pixels experience becomes even stronger. And so we think this is evidence that of a kind of more regional signal that the local forest loss is warming those areas of surrounding forest. And this is a kind of clear evidence of that signal in the observational data. So then we kind of used a range of different machine learning methods to analyze that data and then predict how the warming that we observe depends both on local and regional forest loss. And when we do that, we find that the model can predict the local warming that's been seen in previous studies. So that's seen in the blue line here, and a comparison of a range of different satellite studies that have been published previously looking at the warming due to local forest loss. And then the 2 orange lines are showing when we add in this regional signal. So this shows that that regional warming that the forest loss is causing can increase that level of warming by about 2 to 3 times over what we would experience just with the warming from local forest loss. We can use this to look at what are the benefits to particular regions of protecting certain areas of their forest. So we focus this on the Amazon to look at what were the benefits of the Amazon protected area system on climate outside of those protected areas. So on the left shows the protected area system across the Amazon in blue. On the right shows the observed land surface temperature change outside of those protected areas. And we wanted to say what was the benefit of preserving the forest cover within the protected areas on the climate outside those protected areas. And so when we combine the machine learning model that we used earlier with those different scenarios of forest cover change, so on the left here is the observed warming that occurs outside of those protected areas, about 0.5 degrees centigrade over this 20-year period. So this is from satellite. This is when we model the same response and the same scenario. We get about 0.5 degrees warming as well. And then we can run a different scenario when we simulate forest loss within those protected areas. So that's a scenario of what would happen if those protected areas had not been preserved. And we see a warming of about 0.66 degrees centigrade outside of those protected areas. And so this shows that those Amazon protected areas have caused a regional cooling outside of the protected areas of about 0.15 degrees over this 20-year period. So we think this is evidence that those protected areas are having a benefit to surrounding regions in terms of providing that a cooling benefit that hopefully provides some evidence to countries within the Amazon of the benefits of the local to regional scale of protecting their forests. So the final part of the talk, I want to kind of then take this out a bit further and look at what the impacts of deforestation in the Amazon could be at a much broader scale across the whole Amazon basin through impacting changes in atmospheric circulation. And so this is from a paper that was published last year, which did an analysis of the ClimTip models. And you can see the different models here shown on this plot. And what's shown here is the impact on the moisture budget of large-scale deforestation of the Amazon simulated by those different models. So the important points in this plot to pick out are the change in precipitation simulated by those models. And that's what's shown with the black circle here. So you can see that the models still have this divergent response. Most models predict deforestation is going to cause a reduction in rainfall, but some models predicting that deforestation would cause an increase in rainfall over the Amazon. But then this study also picked apart that signal in terms of changing evapotranspiration, that's shown in blue, and then the change in incoming moisture due to changes in atmospheric circulation, and that's shown in the yellow cross here. And so what you can see is that most of the models predict a reduced ET, evapotranspiration, over the Amazon, but it's quite varied where the models predict atmospheric circulation changes to either drive down incoming moisture, so that would be the yellow cross below the zero line, or cause an increase in moisture. And so this is really a large uncertainty in terms of what the atmospheric response is to large-scale deforestation. So we wanted to look at this in a bit more detail in a regional climate model, and instead of simulating very large change in deforestation as has been done in these ClimTip models, we wanted to look at the deforestation that has occurred over the last 2 decades in the southern Amazon. And so this shows the states of Rondônia and Mato Grosso in the southern Amazon. This shows the satellite observed trend in leaf area index over that region over this period. So a reduction in leaf area index driven partly by deforestation, and then that increase in albedo, that brightening of the surface, again driven by deforestation signal. And then we use the WRF regional climate model to simulate the impacts of changes in precipitation due to that land cover change. And so we found that over this period, there'd been about a 3% loss of forest over this 15-year period. In our model, this caused about a 2% reduction in precipitation, so almost a one-to-one response of precipitation to forest loss. But what was quite interesting was that in our model, we were able to tag the water vapor that comes from the deforested region, and then look at how much of that reduction in precipitation comes from that local changes in local recycling. We found that only about 10 to 15% of the reduction in precipitation comes from changes in local recycling. Most of it is coming from changes in incoming moisture from outside of the region. And that's shown a little bit in more detail on this plot, split up into the dry season, wet season, and the annual signal. And so again, the green bar here is the reduction in precipitation due to deforestation. So we get a reduction in the dry season, the wet season, and at the annual scale. And then the grey bar is the reduction is due to that change in moisture recycling. And again, here you see that reduction due to the change in moisture recycling is a relatively small part of the signal, maybe 10 to 15%. The rest of it is due to this large-scale change in atmospheric circulation, which is in this model driving reduction in moisture flow input into the region. And so that's shown in these yellow bars, this large reduction in incoming moisture. And so I think this kind of confirms that these kind of changes in circulation that could be driven by land cover change could be really important. They could be, in some places like the Amazon, the dominant part of the signal in terms of how land use change is going to impact climate and regional scales. But it's still highly uncertain. And I think this has really important implications in terms of thinking about how deforestation can impact potential climate tipping points. And so this links back to the paper that was published last year. So if we're in a situation where deforestation drives reductions in evapotranspiration, but then that causes further reductions in incoming moisture due to changes in atmospheric circulation, this will cause reductions in rainfall, which will then cause potentially tree mortality and then further deforestation. Then we've got a kind of a positive feedback loop here, which means that we're going to be more likely to, if we're approaching climate tipping points, we're more likely to kind of go over them. If the opposite occurs, where deforestation causes a reduction in evapotranspiration, but then this causes an increase in incoming moisture, as some models predict, then this system is a lot more buffered because we get a reduction in moisture, but then the atmosphere responds to bring in more moisture to offset some of that reduction. And if that happens, the change in rainfall is going to be much more muted, and then we're much less likely to go down over this climate tipping point. So I think the really important thing, I think, is this change in incoming moisture? Does it exacerbate the signal by acting in the same direction as a reduction in evapotranspiration, pushing itself into a positive feedback loop, or does it buffer the system by bringing in more atmospheric moisture to offset that reduction from evapotranspiration? In which case, I think these climate tipping points from deforestation are less likely. So finally, just to summarize, hopefully I've shown some evidence that we can use satellite data to show observed reductions in local precipitation over regions of tropical forest loss over the last 2 decades. And hopefully these are starting to give some evidence of the quantification of that sensitivity that we can use to test climate models. I think we're trying to look at untangling the local and regional responses of tropical forest loss on climate, both on temperature and on rainfall. And I think some of the regional signal from forest loss might have been missed in previous studies due to removing that signal from this nearest neighbor approach. And finally, I think at the regional scale, a really important aspect is how does the atmosphere respond to forest loss? Does it bring in more moisture from the surrounding atmosphere, which could buffer that reduction in evapotranspiration, or does it exacerbate that reduction in ET by reducing incoming moisture, reducing that moisture inflow, which is much more likely to lead to these climate tipping points. And I think that response is still really highly uncertain. So with that, I'd like to thank you very much for your attention, and yeah, really happy to take any questions.
Thank you very much, Dom. That was really, really interesting. And the floor is open for questions. And let's try, we'll try unmoderated. So whatever you have, whenever you have a question, just feel free to just unmute yourself and ask the question. We'll see how that goes.
I have a question. So when you compare all these models, the different climate models, are they different climate models with the same vegetation module, or are they different vegetation modules?
Yeah, so that plot that was showing comparing the different models, that was models that had participated in the LUMET experiments. So they were all different climate models, so completely different, potentially different setup, using different parameterizations for different things, different land surface models, but trying to simulate the same length of a change. So that was prescribed between the different simulations. There might be someone on this call actually that knows a lot more about the setup of those simulations than me, but that's as far as I understand it. So they do have a very different parameterizations of convection, for instance, parameterizations or treatment of vegetation. One of the differences will be how those models reflect that land use change in terms of changes in our albedo, changes in LAI, changes in surface roughness, for instance.
Any further questions?
I have one. Hi, you said in the end you raised this question whether the moisture convergence can partly compensate for the loss of evapotranspiration. Didn't you answer that question already in the beginning? You said that the recycling ratio is 36% in the Amazon, but the response to the deforestation in models and observations is much lower. So that would point to the partial compensation by the moisture influx, right? Otherwise, you could assume that everything that is recycled is not recycled anymore when you deforest. Then you would have a loss of 36%. Some people argue that way, at least. Right? But the actual response we see is smaller than that.
Yeah. Yes, you're saying there's not a one-to-one ratio between change in moisture and change in precipitation. Is that, Doug, I'm not sure if I understand your question.
Yeah, so some people argue that the recycling ratio over the Amazon is 36%. So if you take away the forest, you lack 36% of rainfall. But what we see is in models and observations that although it's uncertain, but the typical response is a smaller reduction in rainfall. Right, so would that point to, would that support the hypothesis that the circulation changes in a way that you get more moisture inflow from the borders?
Possibly, but then also it's possibly because, precipitation is not, if you reduce moisture by, atmospheric moisture by 10%, you're not going to reduce precipitation potentially by 10%. It could be non-linear. So I think it will be those two different mechanisms happening. But I agree with your,
right.
I mean, yeah.
Mm-hmm. Okay, thanks. More questions?
Maybe I could follow up on that very quickly. Just so there should be I really, what I found really interesting in your talk, Dom, was that there was a lot of, and I think this is something that may have been ignored a little bit in earlier studies. And so the question is, to what extent would you imagine that the actual spatial pattern of deforestation or degradation or forest loss would play a role? Like, you know, could one even go as far as saying to, you know, the regional governments, if you have to deforest a certain fraction, then at least do it in this and that way, deciding on spatial scales at which that happens, so that it might actually at least not overall reduce the moisture inflow, but maybe even, I mean, you know, maybe you can't hope for overall enhance the precipitation, but maybe at least keep it at a balance.
Yeah, I think there's been some really nice work by people like Ari Stahl and others who started to look at that by looking at specifically parts of the Amazon where they're very sensitive to both to moisture loss, but also would cause, you know, large changes in downwind precipitation. So I think there is potential to do that. I guess a caveat of those studies is that they do tend to assume that there isn't a change in circulation pattern, that they're kind of, they change the moisture inputs on the surface, but to keep the circulation the same, which is probably okay for kind of relatively small changes in land cover at any one location. But, you know, as we start to change the land surface at much larger scales, then you're going to also impact large scale circulation, which wouldn't be accounted for in those studies, I think.
Thank you. Any further questions? You're also free, if in case your microphone isn't working or so, I mean, you're of course also free to just place your questions into the chat and then we read them for you.
Hi, do you hear me?
Yes, hi Kino.
Hi. Yeah, thank you for the presentation. I have one question. Is there a simple explanation for the hypothesis that deforestation would reduce the moisture inflow, like from a mechanistic point of view? How would that work?
Yeah, so I guess there are, and I guess you could kind of argue in both directions of how that could work. But if you had deforestation that caused a warming of the surface, but a cooling aloft, and that could be due to initially due to a reduction in convection, causing reduced precipitation aloft, that would cause a cooling aloft. That would then cause a reduction in inflow of moisture above the surface, which is probably where most of the moisture is coming into the Amazon. So that could be a way in which it could happen.
Okay, thanks.
Yeah, can I follow up on that? Because I'm also a little confused with that. You started out also with saying that the albedo is different between the forest and the deforested forest, and that would, since you have a higher albedo for the brushland, you would think that that would be cooling because you're reflecting more sunlight. So now the question is, where do you, I guess you measure the temperature from satellites. So this is the canopy temperature you measure over the forest, and the ground temperature you measure in when it's deforested. Is there a difference there, or I mean, how should we think about this?
Yeah, so I think both studies that have looked at satellite data that are looking at land surface temperature, but also, which in a forest is that top of canopy, but also studies that have looked at paired temperature sensors looking at air temperature, tend to show the same thing, that tropical forest deforestation leads to a land surface warming, but also a near surface warming. And that's thought to be primarily due to the reduction in evapotranspiration. And so that causes a shift from latent heating to sensible heating, which causes a warming, which offsets the change due to, is more important than the change due to albedo. So that's the kind of the mechanism through which that deforestation leads to that local scale warming. And I think that signal is quite robust and has been shown by a lot of studies, both with satellite data, but also with using climate station data.
All right, there is it's a question by Sally Soria Deng. If the missing precipitation in a deforested area will be compensated by incoming moisture from somewhere else, will there not be a net loss of precipitation overall, and precipitation will be missing somewhere else?
Good question.
Depends on atmospheric stability as well, I guess.
Yeah. I think I'm going to have to think about that one and not come back with a direct answer. I guess it's sort of a question, as you start to scale up, even to a larger scale, what's the kind of net response at a global scale? I think studies that have looked at that have shown very small impacts at the global scale. So I guess that's answering your question a little bit, but there will be offsetting impacts. And I guess, well, maybe particularly the dominant driver of overall precipitation could be the absorbed amount of incoming radiation, which is linked to albedo. So maybe at a global scale, that could be a primary driver, which would mean you would get a reduction in precipitation globally if you've got a reduction in absorbed radiation by the surface. But again, there's probably people on this call which would know a lot more about that than me.
All right.
I had a question more policy related. Dom, thank you for your presentation. Yeah, I was wondering, so your evidence shows that protecting, right, certain forest areas can help, right, with kind of stabilizing the level of precipitation and temperature rise. As I was wondering, like, have you had interactions? What was your experience like with policymakers in that Amazon region? Is this something of their concern, that the local temperatures are increasing, or that local rainfall is impacted? Is that concern at all? Does this is this a good argument for them in a way?
Yeah, exactly. So I think that's one of our interests in looking at this closely, is because I think, the kind of global impacts of forests in global climate are quite well known. But I think demonstrating those local and regional impacts could have better traction with local policymakers and regional policymakers, because as all politicians, you care primarily about your local constituents. And so if we can demonstrate those benefits at those scales, and I think that could have important policy implications. So I think at the moment it's maybe not so well recognized, or maybe at various different levels by different people. But I think better communicating those benefits at that kind of local to regional scale, I think could have benefits to providing evidence for forest protection.
Great.
Maybe one more from me.
Go ahead.
I'm sometimes wondering how much precipitation loss, let's say per deforested area, makes the forest atmosphere system unstable. Because when I hear 10 or 20% rainfall loss for complete deforestation, in a climate model that probably does not lead to alternative states, because the tree cover is still very high when you reduce it by that much. But maybe in reality, for a forest, 10 or 20% loss is a catastrophe already. And yeah, what do you think? How can we get understanding for the consequences?
Yes, I mean, I think obviously it's going to be really important when that rainfall reduction occurs, and maybe reductions in dry season rainfall and an extension of the dry season are going to be much more important than a reduction in rainfall in the wet season when maybe it's not so important. So I think it's definitely going to be important to understand that better. It's probably going to be very regionally specific. So yeah, obviously parts of the Amazon that are maybe quite close at the moment to that threshold, and maybe parts of the southern Amazon where 20% reduction in dry season rainfall could make a really good impact. Whereas there probably are parts of the Amazon where, yeah, as you say, maybe that wouldn't be so important. How well models capture that as well, I think, is a good question. And there have been some of those really important drought experiments that have been conducted across the Amazon that have started to look, at more detail of how the forest responds to, for say a 50% reduction in rainfall, which have shown, large impacts of that, scale of reduction in rainfall in parts of the central, sort of north central Amazon. But I think that's also a big uncertainty. Yeah, exactly. Is how sensitive is the ecosystem to those climate changes? I guess on top of that, we've got complexity of temperatures are going up from global climate change. They're potentially going up as well due to nearby land use change, and so that could be adding additional stress, moisture stresses and other stresses on the system. But also CO2 is going up as well. So that's another complexity that makes it even more difficult to understand. So that's experiments like Amazon Face, which are going to be really important in trying to understand how the system is going to respond under elevated CO2 concentration. So yeah, in our work we didn't study that part of the cycle at all. So we didn't look at how sensitive the forest was to those changes at all.
Yeah, thanks. Yeah, it's really more complex than a saddle node bifurcation, I guess. Yeah. Thanks a lot.
But I mean, I think that's why, the project that you're working on is super fascinating, because I think we're still, really not sure, is the Amazon, for instance, quite a stable system that can experience, quite large perturbations and still be relatively stable, or are we close to an impending tipping point, which, and we're already very close to that in terms of, people talk about 20% deforestation of the Amazon could push you close to that tipping point. We're very close to that already. And so I think that's why it makes it, super exciting to work on, but really important to work on, because, we maybe don't have very long to get a better understanding of this, to understand where we are on that, between, a really resilient Amazon to one that's actually really sensitive to future change.
I couldn't agree more. Any further questions?
I had a question on behalf of a colleague who could attend because they are in Panama and I think it's quite early there. So it was about climate data, I guess, so for local level decision making. They were asking if there's any databases that could be used to search for climate data, I guess related to local precipitation and temperature changes, or if there are any tips on downscaling climate data. They were mentioning this project called Chelsea, if you have heard about it.
Yes, I mean, again, I'm probably not the right person to ask. I mean, there is really good data, I guess, at downscaling climate data to relatively fine scales, if you're wanting to kind of have information about how the climate is likely to change in your particular region. I guess that's not telling you why that change is happening. Is it happening due to forest loss in the region? Is it happening due to global climate change? So I guess it depends partly what they're interested in. I think in general there's not very much good information at a local to regional scale of telling people, what is the impact of deforesting this region, what's going to be the impact on our local community or, the nearby town in terms of temperature or precipitation. I think that information isn't available, partly because the uncertainties, I think, are still too high, but also because I don't think we're communicating that maybe in the right way to those sorts of people that might need it.
Right. Thank you for answering that. And also related to that, do you, I'm just curious, what was the media response to your research results was like? And also, if there are strategies that you think that could work for scientists to kind of go outside, kind of amplify their impacts outside their direct scientific community?
I think one of the ways we're going to try to communicate the new work that we're working on, which is looking at the benefits of the Amazon protected area system. I think in terms of we're trying to communicate that in terms of positive message around what are the benefits of the things that you're already doing, the policies you've already put in place, the things you committed to as politicians or country. These are the benefits that's providing, and it's sort of a good news story. I think in some ways that maybe gets communicated more easily, and it's people are more receptive to that, to another story that is sort of bad news, sort of hitting Amazon nation sort of stick and going, you're deforesting, you're not doing well, and sometimes that negative message can sometimes not be so productive in terms of messaging. So we're hoping, by communicating, these are the positive impacts of what you're doing, that could persuade people to do more of that and to do that better. And yeah, I guess it's kind of trying to flip that messaging a little bit in terms of focusing on positives to encourage future and more change rather than focusing on the negative stories. And I've just seen someone's answered the question about downscaling data much better than me, so there's a source for that.
Yeah, thank you. I was about
to
hint at that entry in the chat. There is another question, I think, by Bo regarding the communication with policymakers or thought leaders. Do you also draw some connections that there will be more forest fire events, since that will harm local community at another level?
Yeah, that's a really important point that we've not looked at really in this work at all, is those additional feedbacks onto fire. So yeah, fire itself, which is really damaging, but then impacts of that on regional air pollution and human health as well. So yeah, I think there's lots of different ways this could be communicated.
Thank you very much again, Dom. This was really interesting, and also thanks for very interesting questions and a nice discussion. And to everyone, so we will continue doing this on every first Tuesday of a month at 2 p.m. CEST. So stay tuned. We'll send invitations in time. So thanks very much for coming, and have a great afternoon, everyone.
Great. Thank you, everyone. Thanks for your attention and for joining us.
Thanks, Dom.